Welcome to Monday Night Calculus, the spring edition. This is slicing it thin. Tonight we are going to be looking at Riemann sums, and I have got Steve Kokoska and Tom Dick here with me once again. I'm very excited to have them on. I saw that earlier today the student document link that's posted in the description was not working. I fixed that. So hopefully if you are looking to follow along and answer the questions, if you haven't already downloaded that, go ahead and go to that section, the description down below, and you should be able to find the student document so you can see the questions that Steve is going to be working through. Second, I will be posting the solutions tomorrow morning. At some point, I'll be following up with the solutions document inside of this link tomorrow morning, as well as Steve will be posting some stuff out on the Facebook, the Calculus Facebook teachers page as well. So with that, I'll let them get started. Please don't hesitate to put questions and things in the chat. And always keep me honest. I haven't done my homework today, so if
Oh,
Steve has a
no.
question, help me out.
All right. Well, thank you, Curtis. It's great to be back with you and Tom in the new year. We've got some good questions here on Riemann sums, I think. Some calculator problems, some analytical ones too, which I think should not be lost in all of this. So let's start out with a pretty straightforward one, at least until we get to part B. So in context here, we have wheat being drained from a silo at a rate R of T thousands of gallons per hour. Actually, I looked this up and it doesn't sound quite right, but that is a way that they measure wheat coming out of a silo. So this rate is decreasing over time, and the values of the rate at 1 hour intervals are given in the table. And I'm sorry I didn't do this, Curtis, but perhaps I'll do this when I post the final solutions. Of course, these are the values of T in the top row, and the values of R of T are given in the second row. In part A, we want to find upper and lower estimates for the total amount of wheat drained from the silo over this interval 0 to 6. Well, because R of T is a decreasing function, an upper estimate will be a left-hand Riemann sum. So the best we can do there is we can get a left-hand Riemann sum based on 6 subintervals. And I wrote out way too much here because all of the subintervals are 1, so we could have done this a lot easier, but I thought I'd put everything in there for completeness. So value at the left-hand endpoint times the width of the subinterval. Next subinterval, value at the left-hand endpoint, width, and all the way down the line. And multiply, add all of those up, and I got a 19.2. So that's an estimate of the total amount of wheat drained from the silo over the interval 0 to 6. And really, I should probably do something like this too, Curtis. This is an estimate of the definite integral from 0 to 6 of R of T dt. It's an upper estimate because R is a decreasing function. So a lower estimate in this case would be a right-hand Riemann sum. So we're going to do the same thing. We're going to go into each subinterval, but this time we're going to choose the right-hand endpoint, right-hand endpoint, right-hand endpoint, and so forth down the line. Multiply each by 1, add them all up for an 11.6. Pretty good, pretty straightforward, good to get us going early in the morning, tomorrow morning at 8 a.m. Let's take a look at part B. Curtis, I don't know if Mark Corrali is on tonight, but if he is, he would probably appreciate this. I
He
just
is on
discovered
tonight.
he is.
Yes, he is.
I just discovered that with this remarkable, if when you share your screen, you don't have to be connected by the wire. It
Oh, that's
actually
fantastic.
works through the Wi-Fi. I'm sure he knew that. And I think somewhere along the line I knew that, but I discovered that today, which is pretty cool because then you can walk around the room with it. All right, in part B, use a midpoint Riemann sum with as many subintervals as possible to estimate that definite integral, and then use that estimate or use that value to estimate the average value of f over the interval 0 to 6. Okay. So I think the best that I can do, maybe I should arrow up a little bit here. I think the best that I can do is 3 subintervals here. So I can go 0 to 2, 2 to 4, and 4 to 6. So I choose the midpoint in each one of those subintervals. Each subinterval has width 2. Do the multiplication and add them all up. That's 14.4. So that is an approximation to the integral from 0 to 6. And that should be R of t, R of t, et. And now we're going to use that value to approximate the average value. And that would just be 1 divided by 6 minus 0, 1 divided by b minus a, times that estimate for the definite integral. Sorry, that should be an r. And that's approximately a 2.4. That's pretty cool. Now, I have sort of an odd question about this one, Curtis. And I think I've actually seen this done on AP exams, where students are asked to use a midpoint Riemann sum with as many subintervals as possible. I'm going to erase this up here. It seems to me that some students will do this. Well, I can do a midpoint Riemann sum there, and then I could do one here, and I could do another one, and another one, and another one, and stop.
Oh, I see. Yeah.
And so the question is, that seems reasonable. It seems kind of okay. It seems like I can do that. But what's wrong with that, just logically?
Well, you're overlapping, so you're counting, you're double counting sections.
Very good. You're double counting areas, aren't you?
Mhm.
You're double counting areas. Yep. So that's not a good idea. And again, I think I've seen that done. Tom, do you want to do anything with technology on this one?
Sure, Steve.
Okay.
Let's go ahead and take a look at, see if I can pull up my TI-84. You can let me know if that's come up okay.
Yep, you're good to go.
Okay, great, fantastic. So we don't have a function to graph here. We just have a table of values. But on our 84, we do have this stat editor, which lets us work with tables of data like this. And just wanted to kind of illustrate how we could work with this using the stat editor. So I'm just going to press the stat key here. Up at the top, it says edit. And this, when I enter this environment, I've got my lists arranged in columns. And so I'm going to just use list 1 and list 2, L1 and L2, for the 2 actual rows of Steve's table here. So in list 1, let me go over get over to list 1, the first entry. Let me just put in those time values, I think. 0.
Yep.
They're very simple. They're just going up in 1 hour increments. Was hours? Yes, it was hours. Yes.
Yep.
Yeah,
It was hours.
check my time units here. And we'll go up to 6. Great. And then in list 2, we'll put the rate,
Yep.
which were the thousands of gallons per hour. So that was 8.0, 4.8, 2.9, 1.8, 1.1. And thanks for your patience. But I did, just kind of illustrate how quickly you can get this data in there. Now we have, let's see, our complete table of values in lists. And now we can use some of the functionality to actually compute these Riemann sums that Steve was talking about. So for example, now this data here are independent variables time, and it's really nicely equally spaced, okay? But sometimes we have data where the data values are not equally spaced. There's different intervals. And the left and the right Riemann sums, you can do those with the data spaced in any way, any partition. Now the midpoint sums, you're going to have some requirements on how your data is structured. But what I'd like to do, and it may seem a little bit crazy here with this data, but if you think about what would happen if you had unequal data, is I want to get the my delta x, if you will, or delta t in this case. What's the width of each subinterval? Okay, now here we can just look at it and see that it's 1. But let's say it wasn't equally spaced. Well, if I go over to L3 and go up to the header there, L3 up there, okay, I'm going to define L3 by using, I'll go to the stat editor again, go to, excuse me, let me go to second stat, which would be lists, and go over to operators. And if you look down there, look at number 7, there's delta list. And we think of delta t, delta x, whatever. This is going to give us our increment values for our list. How far apart are each of the entries spaced apart? So let me go down and choose delta list. And I'll put in L1 now. So that'll be the second shift of L1. Enter that. And again, this may have seemed a little bit silly to do because we could see these increments are 1. But again, I would remind you, if any data that you would have, it would compute all of those increments for you. And so now that we have those increments, we can do left Riemann sum, right Riemann sum, and the midpoint sum we'd have to be a little bit more careful about. Well, let's go ahead and do a left Riemann sum. So really what I want to do is take the left endpoint of each subinterval and multiply it by the width of that subinterval. So that means I'm going to take the 8, the 4.8. I'm going to use all of these values except for 0.4. Okay. So what I'm going to do here is I kind of need to throw that last value away if I'm going to do a left Riemann sum. So I'm going to go over to L4. And let's just go ahead and make it equal to L1. Excuse me,
L2.
not L1. How about L2? There we go. There we go. And I'm just going to throw away the last value. So I'll go down to 0.4 and clear that out. I think. Let's see.
There you go.
And let's see. I think I just hit enter now. There we go. So now I just have the left endpoints. And for do that left Riemann sum, we just want to multiply these increment values, the 1s, times these values and add them all up. So what I'm going to do is go ahead and quit to my calculator page or calculator screen. And we'll go to the list math. And you'll see number 5 there is sum. And we're going to multiply that list 3, which was our increments, times our list 4, which were our left endpoint values. Fingers crossed, what this does is multiply those together and sum them up, and we should come up with exactly what Steve did. My fingers crossed, do we get that 19.2? Looks
Indeed.
good. Okay. And if I wanted to do a right Riemann sum, I won't go through that whole thing, but if I went back to my stat editor what I need to do is copy L2 again, and this time throw away that very first value of 8, because that I won't use that first left endpoint. But all the other values now are right endpoints of those intervals, and I can do that right Riemann sum. For the midpoint sum, frankly, for this data, I think I would just kind of pick those values out and do a sum. It's really only 3 terms, I think.
Yeah.
And evaluate it that way. But if you had a longer data set, you could still manipulate these lists in that way. So I'll, at that point, I think I'll turn it back over to Steve, unless, Curtis, you've seen something come up in the chat that I should address, or if either of you would like me to do anything here.
No, I mean, there was some discussion about, you could actually use the setup editor. So we were talking about named lists in the chat. You were working there, and you could name a list and name it left endpoints, and another one for right endpoints, and another one for the intervals themselves.
Absolutely.
And you could actually use the setup editor and make sure that those lists live on the screen all the time, so you could see those named lists and replace list 3, 4, 5, 6 or whatever with named lists, and make sure that those actually showed up. So you keep list 1 and list 2 and then name some other lists. That's another way to do it. I don't know that we have to do a demonstration of that, unless somebody just really wants to. They can send a chat message, and maybe we can do a demonstration of that later, or I could even send them a video if they want. But otherwise, yeah, we're just looking at this. I do have one question that popped up and said, you could also put a 0 in instead of deleting the endpoint. I suppose you could put a 0 in and multiply that first term or the last term. I think that might, I guess.
Yeah, actually that had occurred to me, is just keep L2 intact.
Keep L2 the way it is and put a 0 on one end or
play
the
with
other end.
L3 a little bit. Yeah. So you could put a 0 as your first value in L3, and all the rest ones that would pick off the right endpoints.
Yeah.
Or have the last entry be a 0 and all the others be 1. That would pick off all the left endpoints.
That would pick off all the left endpoints. Right.
Yeah.
Right.
Yeah,
and there's also one more comment. There is a program running around out there for the TI-84 plus CE that will actually do Riemann sums as well. So I'll see if I can find. I think we actually have a copy of it on the website somewhere. I'll see if I can send a link to it in the chat while Steve gets on to the next question.
Okay.
Sure. Sounds good.
Thanks, Curtis.
All right. Yep. So I'll stop the share and turn it back over to Steve.
Okay. All right. So the function f here in number 2 is defined as the square root of x times the log of x. And R is going to be the region bounded by the graph of f, the x-axis, and the lines x equal 1 and x equals 6. So I've sort of drawn a picture of this region R down here. I want to find left and right Riemann sums to estimate the area of this region R for n equal 10, 30, and 50. I want to sketch a graph to illustrate R sub 10, and I think eventually I might even be thinking about finding the exact area of that region.
Excuse me, Steve, have you shared your screen again?
Yeah.
He did. He did.
Okay.
I can see it.
Oh,
It
interesting.
did.
Okay, I got it. Sorry. Okay.
Yeah, that's all right.
For the interruption.
No sweat. No sweat. Okay. So for this one, I could, and I think it's a good exercise for students to write their own sort of Riemann sum functions. I think that just solidifies an understanding of the formulas, the expressions, what they're doing, what they mean. But there is a nice TNS file on the TI website where you can change the function f, change the interval, change left, right, midpoint, and trapezoidal sum, and change the value of n. And this will give you the exact and the approximate area. So I used that TNS file. Oh, and I'm sorry, Curtis. By the way, we're not talking about limits tonight, but this is kind of an interesting one. I wonder what's going on over here with this function as x approaches 0 from the right. Because I know the log function is not defined at 0. I wonder if we could figure out that limit. We'll leave that as an open question, okay? All right, so I used this TNS file in order to determine these Riemann sums. So in the top row, I think I have n equal 10, and the left Riemann sum on the left, how about that? And the right Riemann sum on the right. So I don't know if you can see that 10 point, is it 366? And 12.561. And then what I did, of course, I had already input the function, but I had changed the values of A and B. And then what I had to do was to manipulate this value of n down here. This is a slider. And so I changed n to be 30. You'll notice it's drawing the 30 rectangles, which is pretty cool. You can imagine that this is going to get pretty dense in a while. And there's the left Riemann sum. What is that, 11.102? And the right Riemann sum is 11.833. I'm feeling pretty good about this. It does sort of feel like these two values are sort of zeroing in on something, some number. And then I finally changed n equal to 50 down here. And I got my left and right Riemann sum. And what I tried to do is to summarize all of that in a table down below. So there's the left and the right Riemann sum for n equal to 10, 30, and 50. And again, I think it would be a good exercise for students to write their own function to determine these values. Okay? All right, well, let's see if we can find the exact area of this region R. Curtis, we don't have the opportunity to do too many BC problems, but this is a BC problem. So it's not a bad one. Let's take a look at it. The area of that region R would be the definite integral from 1 to 6 of the square root of x log x. So how do you integrate that? Well, the technique is integration by parts. And it seems a little weird here, but what we do is we let u be equal to the log of x. Why? What's the problem-solving technique there? Well, the reason for that is when we differentiate both sides, we sort of get rid of that transcendental function and change it into a rational function, 1 over x. And that's a good thing. Even though dv is equal to x to the 1/2, and when we integrate that, we have increased the power on x. This still seems like it's a good thing to do. So let's see what happens here. This would be equal to u times v minus the integral of v times u. All of that evaluated from 1 to 6. Let's see, I did a little bit of simplification in there. I've got to find an antiderivative. It's x to the 3/2 over 3/2. So there's another 2/3 there. And let's see, I did a little bit of simplification and I have to evaluate that expression, that antiderivative at 6 and 1 and subtract. Okay. I did that. There's my analytical expression. And yeah, Curtis, you're right. I probably could do a little bit more simplification there, but that's not too bad. Plus 4/9 at the end, I guess. And that's approximately 11.468, which if you go back to the previous slide is really close between those two values, those two Riemann sums. And here to me is one of the most amazing things here about technology. On the TI-Nspire CAS version, I input or define this function f, and I can actually find a symbolic antiderivative and a symbolic answer, the exact symbolic answer. That's just absolutely amazing to me that we can do that. And my trick in order to convert that into a numerical value is to take that value and to multiply by 1 dot, okay? 1 with a decimal point after it. So there's the 11.468.
Wow.
I like that problem. That's a good BC problem. Integration by parts, classic problem-solving skill there that you need to let u be equal to the log of x. Good question. Tom, do you have anything on this one?
Yeah, Steve, I think
Okay.
so. Let's
Okay.
go ahead. All right. So I'll bring up my 84 again and get out of the list editor there. And just wanted to illustrate for people. You can and this was just a real revelation for me when I first started using graphing calculators, is a chance to actually work with some reasonable partition sizes on Riemann sums.
Yeah.
When
Yep.
you do these by paper and pencil, you can only do just 5 or 6 subintervals, whatever, and it's just kind of an exercise in calculation torture sometimes. But what I'm going to do is just show how we can build up a Riemann sum fairly easily. Yeah, and I'll use your function as an example. Maybe to start out with, why don't I go? Oh, it looks like I've got a bunch of stuff in here. Let me clear this out.
Wow, Tom, what you been up to?
I'm not sure what was. I'll get rid of that. Here we go. All right, in y1, I'll just go ahead and put square root of x. And get out from under the square root sign and times the natural log of x. Okay. So that was our function. Just for a quick reality check, why don't we go ahead and graph it in I'll do a zoom decimal window. I think that'll be a actually decent window for this. Yeah, it looks pretty good.
Very good.
So, and it even reaches from 1 to 6, so we can see the interval of interest here. So in building a Riemann sum, let me just go back to the calculator screen. We've got our function in y1, and I'm going to do some preliminaries here. One thing we'll need to do is let me go ahead and look at my 2 endpoints and store those values away. So I think the first endpoint, I'm going to, let's see, that was 1. I'm going to store that in A.
Okay.
6, store that in B. And if I do other integrals now or Riemann sums, I can just change my values for A and B. Let's see, another thing would be the partition size. So for example, here, I think you start out with 10 as
Yes.
one of the sizes. So let me take that 10 and store that in N for the number of partitions. And what we'll need to do is subdivide our interval from 1 to 6 into 10 equal pieces. Now the size of those pieces is our delta x. And we can calculate that by just taking b minus a. And divide by n. And I'm going to go ahead and store that in D for delta, okay?
Okay.
All right. And quick reality, that makes sense. My interval was a length 5, divided in 10 equal pieces. They should each be 0.5. Okay, so what's a left Riemann sum going to look like for this function? Well, for that, we're going to want to go to our list thing again and actually go to math and we'll do a sum. Okay. So I'll pull up number 5. There's sum. And the sum we're going to sum a actual sequence of values that we get by calculating each of the, let's see, what will we do? We're going to take, we're going to evaluate our function at each left endpoint, at each subinterval, and then we're going to take each of those values and multiply by our delta x, and then we're going to add those all up together. So what I need to do is make a sequence. So I'll go back to list, operators number 5. And my expression, I'm going to use k for my index. All right, so that'll be my variable. And so the expression I'm going to use is, let's do y1 of, let's see, for left endpoints, I'm going to start with A. And then as k increments, maybe I should go ahead. So my variable will be k here. I will be moving by delta x each time. So I'm going to start with the left endpoint. My k value, I'm going to start at 1. And you know what? I'm going to go ahead and fill those in because I'm afraid this will be confusing if I don't. Okay, so I'm going to start, k is going to start out at 1. It's going to end at n, which happens to be 10. And the step value will be 1. Okay. Now I'll go back to the expression. So my expression will make more sense now. So I'm going to take k minus 1. Excuse me. Go ahead. Times d, that's my delta. And I'll close off the parentheses. So I just want you to notice, so k, when it's equal to 1, my first value will be a plus 1 minus 1 times d. Well, 1 minus 1 is just 0. So my first value will be a. What happens when k equals 2? Well, I'll get a plus 2 minus 1 times my delta x. So that'll be the next left endpoint. And when k equals 3, I'll be to the next one. So it'll just count through those. Now, those are my y values. So I want to multiply those by my delta value. And that's it. So those are the values that'll calculate my Riemann sum. So let me go down to that bottom line paste. And now we see it pasted into the calculator. And when I hit enter, I should get the value that Steve got.
Yeah, pretty good.
All right. Now, what's nice about this is for that function, now I can just edit. For example, if I changed n, I could then recalculate d, then just edit my sum. So I could very easily edit this to do left Riemann sum for n equals 30, n equals 50. Similarly, if I want to do right Riemann sum, the only difference in this expression is instead of k minus 1, I'll start with k. And so that will take off each of the points. So I just want to illustrate, and for sure, you can get some kind of nice program, but I actually think it's kind of instructive to build these things up from scratch, so you see exactly what you're doing. And as I said, this would, even for this would have been with a scientific calculator. I could have calculated all this out, but it would have been taking me half an hour, I think, to do this one Riemann sum. And this was one that it'll be just as easy to do it for n equals 50, 100, whatever. So it's nice. I think with that, I'll go ahead and stop.
Wait a minute.
Yeah,
Tom,
sure.
would you be kind enough just to show how you would go about changing that n to say 50 and what you'd have to do to change D and then compute a new left Riemann sum.
Sure. So I'll do a 50 and store that in N.
Okay.
Now I need to recalculate my delta because I got a lot more subintervals now. So let me just use my up arrow and go to that B minus A over N, store D. And let me just hit enter, it'll paste that down and recalculate. Okay, notice my new delta is this 0.1. All right.
Okay.
And now let me go up to the actual Riemann sum. And let's see, N has been updated. D has been updated.
Okay.
I think we're ready to roll.
Okay.
So let me try it, see what happens.
Right on the money.
Boom.
Pretty cool.
You see, yeah, once you've taken the time to do that, build that one, you can kind of very easily edit it. Yeah, I just found it fascinating. It was really, I taught calculus for years where this was, I mean, we always did Riemann sums, but it was like kind of torturous. It's like, where when do we get to the shortcut? But now it's really a reasonable way to, especially with functions that are expressed in terms of data. You don't have a formula where you're able to use the fundamental theorem. Riemann sums can be a very practical way to get an approximate answer. Okay. I'll stop the share there and turn back to you, Steve.
All right. Tom, I may need a little help on this number 3.
Okay.
I like this problem. So we have this function f, which is decreasing, continuous positive, and concave up on this interval a to b. So those expressions, ln, mn, tn, and rn are the left midpoint, trapezoidal, and right sums for n subintervals. So which of these inequalities is true? We want to place these values in an order. I don't know. Can you see the color there, Tom?
Yeah.
Okay, good. Good. So the blue curve is, well, the curve F. If I've drawn it right, it is decreasing, continuous, positive, and it's concave up. And if I've done everything correctly here, the left-hand Riemann sum is certainly larger than the right-hand Riemann sum. So I feel pretty confident that I'm going to be putting those two values like that, one on the left and one on the right. Right Riemann sum on the left. And I think I can see those two. I think I can see those two. Here's the left Riemann sum. I'll color it a little bit there. Here's the right Riemann sum. Yeah, I can see that. Okay, let me erase that. I can see that one. Now, what about the trapezoidal sum and the midpoint? Well, this line, which I think is maybe brown, this one right here, is representing the trapezoidal sum. And this one right here is representing the midpoints. So I've taken the midpoint and I've gone up to the value on the curve. Now, in each one of these subintervals, which of those which of those regions is bigger? Well, I think, Tom, if I remember correctly, I think you showed me this trick. I think if you take that line right here that represents where the midpoint sum is, and you tilt it a little, right?
Right.
You tilt it right on this point right here. It'll eventually come out like this. And you'll see that that area is actually less than the trapezoidal area. So I don't know if I have a better explanation for that. but I think that's the correct order of those terms. Curtis, you okay with that?
I am.
Oh,
Sorry,
okay.
I had myself muted there for a second.
All right. Cool.
Steve, if you want, I've got a TNS file that actually illustrates that
Oh, very cool.
dynamically.
Yeah, yeah. Okay, cool. Okay.
All right, if I pull that up.
Yeah, I'd like to see that again.
Okay.
All right.
Let me see if I could pull that up. So here, can you see my TNS or TI-Nspire screen here?
Yes, yes.
So I've got a curve here, and it's actually showing the area under the curve. But this issue you said, well, exactly how does the midpoint rule value compare to the trapezoidal rule?
Right.
Even if the function's monotonic, like in this case, it's decreasing over the whole interval. Trapezoid and midpoint are both going to be somewhere in between the left and right endpoint values. So,
Yep.
so
Agreed.
let's take a look at the value at that midpoint. And there's that midpoint rectangle. And I'm going to take the top of that rectangle and use the midpoint value that's on the function curve as a pivot. So I'm just going to swing it like a propeller where that's the center point. So you can see it start to rotate there.
Yep.
And what I would maintain is that the area, that orange area doesn't change because that part of the line that swings down evacuates some area that is made up for on the other side of the pivot. Okay, so the area of that trapezoid is always the same. And so I'm just going to keep pivoting until it's tangent to there at the midpoint. And that's going to be parallel to this trapezoid value. Well, but it'll be above. It'll be, we can see that the midpoint, that orange trapezoid has the same area as the midpoint rectangle. So here we can see that the midpoint value was definitely bigger than the trapezoid value.
Which is pretty cool.
Yeah. Now, if that curve had been concave in a different way, like here's one where the curve's concave up. If I go through that same pivoting, now my midpoint value is less than the trapezoid value. And what's really interesting is it's on the opposite side of the true area value as the trapezoid. Now that's provided it's concave up the whole. The concavity has to be not changing over that.
Right, right.
But I always thought this was a really cool illustration of how you can see the relationship between midpoint and trapezoid by visualizing that pivot, which was exactly what you were trying to describe, I think.
That's cool.
All right. I'll
Very, very cool.
turn that back over to you, Steve.
Okay, thank you. Okay, Curtis, we have a couple of problems here. These types of problems usually appear on the exam in the multiple choice portion. And in these kinds of problems where we're looking at this limit of a Riemann sum, sometimes there's more than one answer. So I'm going to show you my answer, but you may, I'm sure when you work this out, you may have got a different answer than I did. So we're going to try to describe a region whose area is given by this limit. So it's the limit as n goes to infinity of a sum from I equal 1 to n of the cube root, holy Toledo, of 1 plus 4i over n times 4 over n. Okay. Well, I probably should have kept this until the very end, but this does represent, in my opinion, the area of the region lying under this graph, the cube root of 1 plus x on the interval 0 to 4. How did I get that? Well, I look up here at this expression, and the very first thing I want to try to identify is delta x. So delta x is equal to 4 divided by n. Now I want to look for some way here to find this x sub I. Oh, pardon me. Yeah, this x sub I. So let's see. I think one way I can do this is to write x sub I is equal to 0 plus I. Tom used k. I tend to use I here. Times delta x. So the 0 doesn't matter. I times 4 over n. And there's my x sub I right there. X sub I star or x sub I. So I identify what delta x is, and I somehow try to find an expression for x sub I, identify what a and b might be. This is going to be a. And what's b here? Well, what happens to this expression as I goes from 1 to n? Well, let's see, it goes all the way up to 4. So that means that b has got to be equal to 4. So this indeed does represent the area of this region lying underneath this graph, the cube root of 1 plus x on that interval 0 to 4. These are sometimes tricky. I look for an expression for delta x, and then I hope that that leads me into what a and b are. And then I hope that that leads me to what the function is. Let's try one more.
Say, Steve, would it be okay if I jumped in there on part?
Sure, please.
I don't have a technology thing to show, but I find this kind of fascinating. Is I actually came up with a different answer than you.
How about that?
Yeah. So the way I looked at it was I did see that delta x that you were talking about. It looks like it's 4 over n.
Okay.
Which is telling me, okay, my interval must be of length 4 because I've divided it, chopped it into n pieces, so 4 over n.
Right.
And the first value I was thinking of was actually, well, if my left endpoint, if I was 0, my left endpoint, that thing under the cube root sign would be 1.
Mm-hmm.
So I was thinking the function could be the cube root of x and the intervals 1 to 5.
So here's an interesting question then.
Yeah.
I wonder if we integrate both of those, do we get the same answer?
Yeah. And I think there's just kind of we look at the graphs of those two functions and the two intervals.
Yeah.
So there's kind of a simple, just a horizontal shift going on, and
Yep.
they really are exactly the same areas. So, and I wouldn't say one of those answers is superior to the other. There's actually probably, I'm guessing, lots of other answers too. These are probably the two most natural ones, or the ones.
I agree.
So.
Okay, cool. And here's one that's a little bit more complicated. So this expression, I think, represents the area of the region lying under the graph of y, holy Toledo, the tangent inverse of the log of 1 plus x. How did I get that? Well, I isolated my delta x, that's 2 divided by n. And again, I did it this way. I looked at 0 plus I times delta x was equal to 2I over n. So I see this as a, and b is going to be 2. And therefore, this represents the area of this region under the graph of that expression on the interval 0 to 2. And Tom, I'm sure you got a different answer for this one.
I sure did, Steve. Guess what it was. Yeah, my interval went from 1 to 3 instead of 0 to too. So,
Pretty cool.
but it is neat. Yeah.
Okay. Couple more here. So let's use technology to find left and right Riemann sums for this function over this interval 0 to 2. And we're really going to stretch the calculator's limit here. We're going to use n equal 100 equal subintervals and explain why these estimates show that that inequality is true. Okay. So here's what I did first. I took a look at this function and found its first derivative. And I noticed that the first derivative was always positive. That means that the function is always increasing. If that's true, then the left-hand Riemann sum is always less than the right Riemann sum. And the left Riemann sum is always less than the definite integral, the actual area, which is less than the right Riemann sum. So that's a little extra step I had to do here. And then I went back to that TNS file that we talked about earlier, changed my function to x divided by x plus 1, changed to n equal to 100. Kind of tough to see all those rectangles in there, but they're there. And I got the 0.895 and the 0.908. How about that? So a little extra here to show that that function is increasing, which allows me to show that inequality. That's neat. And Curtis, I've got one more for you here, and we'll call it a night. Let's let f be defined by this function and let P be a regular partition. By the way, what's a regular partition, Curtis? So you're not talking to us anymore?
I'm going to
Sorry,
get
I'm not talking
equal.
to you anymore. I'm muted.
Okay.
What was your question?
So what's a regular partition?
Regular partition. Let P be a regular partition with equal subintervals.
Very good. Excellent.
I
So
had to read your question there. I wasn't doing my wasn't doing my homework. Mark is telling me to say same. Regular partition seems like it makes sense. Equal subintervals.
okay,
Subintervals.
let's see if we
same
can
one.
find a right Riemann sum for this partition. Okay, so we go into each subinterval, we evaluate the function at the right-hand endpoint multiplied by the width of each subinterval. Again, in this case, each of the subintervals has equal width, 0.5. And I added them all up and I got a minus 6.565. So I have a picture of the rectangles there. Wonder what happened. I don't see a rectangle from like 2.5 to 3. What happened to that rectangle?
It's there. It's just very, very short.
Very short because
Very
we're evaluating at 3 and the function is 0 at 3. So it's a very short rectangle. Okay, I actually used that TNS file once again on this problem. And there's the function. There's the A and the B, 0 to 3. There's the right Riemann sum, minus 6.562. And I still think there's value in doing this. Let's use the limit of a right Riemann sum to evaluate this definite integral. Here we go. A is 0, B is 3, delta x is 3 minus 0 divided by n. X sub I is A plus I delta x, so it's 3i over n. So this definite integral is equal to this limit. I get asked this question frequently. Well, if you write the limit once, do you have to carry it all the way down? Well, yeah, you do. Once you have to carry that limit until you actually do it, until you execute it. So let's see. I plug these expressions, x sub I, into the function. So it's x cubed minus 3x squared. times delta x. And I did a little bit of simplification. The 3 over n are constant with respect to the index of summation here. So the 27n cubed comes out, 27n cubed over there also, I think, because let's see, there's a 3 there. Yep, there's an n squared in the denominator. Sorry about that. And now what do you do with these expressions? These are what we call common summations. Would you have to remember these on the AP exam? Probably not. But this is a good exercise here. So this summation from I equal 1 to n of I cubed turns out to be that closed form expression. We get rid of the summation. The sum from I equal 1 to n of I squared is that expression. Pretty cool. Multiplied out. Then I divided by the n to the 4th here. So I've got this expression, and now I'm going to let n go to infinity. As n goes to infinity, these expressions go to 0. I'm left with, let's see, 81 over 4 minus 2 times 27 over 2, son of a gun, minus 6.75. That's a cool problem. We got a pretty good estimate, didn't we, with just 5, 6 subintervals, didn't we? How about that? Pretty good, Curtis. That's all I got for tonight. Some pretty good technology in there. Some good problems for tomorrow morning at 8 o'clock.
Yes. Well, everyone, I just dropped my email down in the chat box, so hopefully you should see that here popping up in just a second. And if you want credit for watching this session, you can always email me, and I will send you a link to make a professional development certificate. So hopefully you find these sessions really valuable. I've given some prompts again, just to remind you, invite your students, have them log in and watch these sessions, ask questions. I'm always here to pass on the questions along to these two guys. And actually, there's a whole lot of other teachers who are on the sessions in the evenings. Many of them are College Board readers who have been reading for a long, long time and have a lot of expertise. So a lot of expertise out there in the chat box that your students have access to if they want to ask questions. Everybody on here is ready and willing to answer questions as needed. So love to have your kids on here and asking stuff and try to help kids out. Last but not least, we'll be back on here in 2 weeks. No, 3 weeks from today. 3 weeks from today on January 27th. So I know if you've set sort of a recurring meeting on your calendar, just know that the next link is not 2 weeks from tonight, but 3 weeks from tonight. But same time, same place. The link should be public, but if it's not, I'll make sure that it's up there and public in the morning. So we'll have that ready to go. And I will see you guys in about 3 weeks.
Great. Thanks, Curtis. Thanks, Tom.
Thanks.
All right.
Very nice. Very nice.
Very nice session. Boy, that was a really good